Students, I hope everybody is fine. And in this video, I'll be talking about time dilation. We have already discussed Lorentz transformation equations and and length contraction. And what we have understood is that the length of a rod is not constant. The length of a rod decreases when it moves along a particular direction. In our case, it was along the direction of x. Then, in that case, the length of the rod that was measured by s comes out to be smaller than that of the proper length of that rod. So now, another consequence of Lorentz transformation equations is the time dilation. It's a very interesting topic, and to understand the time dilation in a mathematical way, what would be right to say is that we have the two frames of references. It will be a better start for it, and and the time interval between two events is measured with the help of a clock in this case, and the clock at rest in the frame of reference is called proper time. So clock at rest in a frame of reference is called proper time. Right. Now, one of the very interesting consequences of the Lorentz transformation equations is the elongation. It's the elongation. It's the elongation, or we may call it dilation. Dilation of time. And if we consider the two similar clocks, one at rest in the frame S and the other in the frame S dash, which is moving with the velocity v. The clock that we have, it's moving with velocity v relative to S frame of reference. Now, let us assume that the two events occur at the same point. Now, the instant of occurrence of the events, as it is measured by the clock in frame S, or from S, the instants of time, say, measured by the clock are T1 and T2. And that in the frame S dash, the instants of time that are measured are T1 dash and T2 dash. So now we can immediately think of Lorentz transformation equations. So applying Lorentz transformation equations. All right, so that's fine. So what we will have for T1, we will have T1 dash plus Vx by C square. Okay, let it be Vx dash, divide by under root of 1 minus V square by C square. And for T2, what we'll have T2 dash plus Vx dash by C square by under root of 1 minus V square by C square. Now simply what we would like to do is to subtract the two. So what I'll get T2 minus T1. So T2 minus T1 will come out to be T1 dash minus T2 dash divided by under root of 1 minus V square by C square. Or I can simply say delta T is delta T dash by under root of 1 minus V square by C square. That should be the case. Now, from this equation that we have, either you talk of this equation or you talk of this equation, it's clear that this delta T that we have, it's greater than delta T dash. Or I should say that the time recorded in the stationary frame of reference, S, is more than the time recorded in the moving frame, S dash. So what we can say here is that the moving clock, the clock that was in motion, it appears to run at slower rate, and and the time dilation becomes significant uh, uh, only when the relative velocity approaches to the velocity of light. So now, for the sake of argument, now if the velocity of the moving object becomes equal to that of the velocity of light, in that case, this delta t dash will immediately this delta t dash will immediately be equal to zero, and or in other words, we should say that the passage of time or the process of aging shall stop completely. Process of aging shall stop in this case. And if we assume that v is the velocity with which the clock in s dash is moving is greater than that of c, which is not possible because the limit for the speed of any object that we can have cannot cross the speed of the light. So if we assume, at least from mathematical point of view, that this v is greater than c, then there will be what's called as time reversal. There will be time reversal. How would I make an argument about time reversal is that it's like today I'm going out in a spacecraft, and my spacecraft is moving with the speed greater than that of speed of light, and uh, I will come back yesterday. I'll come back. I'll come back yesterday. That's how we can think about the time reversal. What the equations are telling us here, that if this v is greater than c, then on account of time we will have time reversal. And if I leave today, I will come back yesterday. So if today is Sunday, uh, I'm moving on Sunday, and suppose this is Sunday 4th. I will come back Saturday 3rd. So this is how we can understand the concept of time reversal, which is purely mathematical in nature. And, and then there is another consequence of this time dilation, that is what is called as Tivin paradox. Tivin paradox. Okay, now if I assume that we have two persons, and the name of one person is, say, for example, A, and the name of another person is B, and they are twins, and their ages are, say, for example, 25 years each. And now what they do is they decide to learn about time dilation. Now one of them, say A, this A, he sits in a spaceship, and this spaceship travels. It can travel with the speed of the order of, say, for example, 99.98% of c. C is the speed of light along x direction, and having all the things with him, food and bathrooms and all of these things, and this he's having this arrangement, say, for 1 year, and B remains on Earth. So B is on Earth. So A is gone and B is on Earth. B is on Earth, and monitoring this. B is monitoring A. It's monitoring. He's monitoring his space travel. Now, twin A comes back on Earth after 1 year, as per his clock. He's carrying a clock, and he is coming back in an year to the Earth. And A says that he is 26 years old. So A is telling him, A is telling B, I am 26 years old. Now the question is, what is the age of A that's being measured by B? according to time dilation. So that age we can calculate by the equation that we obtained. Delta t is delta t dash by under root of 1 minus v square by c square. That is 99.88 c square by c square. And this is going to come out to be 1 by 0.02, and this will be nearly equal to 50 years. So according to B, the age of his twin A is 50 years. So B says that his twin brother A is that means he is 75 years old. So this is how it comes. Now the point is that what is important for this experiment is it is a paradox because if the spacecraft has to move in the outer space, it has to undergo accelerations, and the equations that we have discussed, they are valid for inertial frames of references. And for a person in a spacecraft, his spacecraft has to accelerate, and these equations are not valid for acceleration. So from that point of view, it's a paradox. But at the same time, if B is able to achieve, B is able to move from the very beginning with a speed close to the speed of light, so that there is no acceleration, then the results obtained here, these results should remain valid under those circumstances. If B is moving in inertial frame of reference, where there is no acceleration at all, acceleration is constant throughout his motion. That could be that's what could be said about it. To what extent I feel I understand it, and and then this is what is called as Tiven paradox. So let us stop here.